Hello my dear students, welcome back to NEET World. So this is our session for IP and EAPCET, JEE and NEET exams. Okay. So when it comes to special discussion for IP, yes, we have, see, every day we will be making two sessions. One session is for IP, right, and one session is for JEE, EAPCET and NEET exams, right. So yes, so IP sessions, exclusive IP sessions will be conducted during morning times for chemistry, particularly I am saying about chemistry. So one day it will be first year syllabus, first year IP, and the next day it will be second year. Like that, alternate days we will be making for first year and second year IPE, particularly for chemistry subject, right. So in the same way we will be having discussions for physics, mathematics and your biology subjects also if you are a BPC student right now. I hope you are watching these IPE sessions and you are utilizing for the your preparation process, right. Now you can utilize this like whatever live sessions we are making for IPE preparation, okay, and to get a material for your IPE preparation, just go to the Play Store and download MedWorld app. What you can do? Download this MedWorld app. Okay, from this MedWorld app you can access free like modules, study materials or study modules for your IPE preparation. So in the MedWorld app we have provided free study modules for your IPE preparation. What to do? Download MedWorld app. So just go to chart section and mention hi in the chat box. Then our team members will guide you how to access this material through this chart. Okay, right. This is about your IP study materials. Yes, in the chat box someone is hi sir. Yes, hi dear, just follow this session. And here we will be discussing, this is our exclusively EAPCET session, as well as the same way it will be useful for your JEE and NEET preparations also. Okay, and particularly today we will be discussing about haloalkanes, haloarenes chapter. Okay, so now first of all, what do we mean by haloalkanes and haloarenes? See, haloalkanes, what they mean here? Alkanes, we know general formula as CnH2n plus 2 right now. So from these, at least one of the hydrogen if I remove from this, see how many hydrogens are there? CnH2n plus 2 hydrogens are there. If I remove one hydrogen from this, so it becomes CnH2n plus 1 because one hydrogen is removed. Now in the place of that hydrogen, I removed one hydrogen and into that place I am adding one halogen like chlorine, bromine, fluorine, iodine, like that. Okay, so it now the formula now becomes like this: CnH2n plus 1 dot X. Okay, it means one halogen is attached here. Okay, so this is a example of haloalkane. So it can be one halogen replaced by one hydrogen can be replaced by one halogen. It means in the place of hydrogen we are writing one halogen right now. So it can be called as monohalogen compound. Like that, if I replace two hydrogens with these halogens, then it becomes dihalo compound. If it is 3, yes, trihalo, tetrahalo, polyhalogen compounds also we have. Okay, I hope you got what do we mean by haloalkane. So the simple example here I am taking C2H6. This is ethane, right? So from this I am replacing one hydrogen from here, means removing one hydrogen and placing there one halogen like chlorine, let us say. Now what happens when we remove that hydrogen? It becomes C2H5, right? So in the place of that sixth hydrogen I am placing one chlorine. So C2H5Cl. So what is this compound here? Ethyl chloride. What is it? CH3, CH2, Cl, right? What is this? It's an ethyl chloride, right? Yeah, this is the formula of haloalkane. Okay, is this clear or not, guys? Whatever we are starting started this discussion, whatever we discussed till now is clear, right? Now when it comes to haloarenes, what do we mean by haloarenes? See, arenes means like aromatic rings, something like benzene ring I can say. So this is a arene. So on this benzene ring, on each carbon there is one hydrogen, right? On each of these 6 carbons we have one hydrogens. So that we got a formula as C6H6 for benzene, right? So from this C6H6, now if I replace at least one hydrogen atom by one halogen, I am removing hydrogen, replacing that with one halogen. Now what it becomes? C6H5X, right? So like this. So for example, I am replacing this hydrogen with one chlorine. Now what happens here? On benzene ring we have one chlorine. So chlorobenzene, what you can call it as chlorobenzene, na? So you can say halobenzene or chlorobenzene, that is nothing but haloarine, chloroarine, that is chlorobenzene here. So these are some examples of haloalkanes plus haloarenes, right? Now everything that we have discussed is clear, right? So there is a small classification of this compound. See, it can be if one halogen is there means mono, if two halogens are there means dihalides, okay, three means are there means trihaloalkenes, you can call like this depending upon number of halogens present. Next one here, based on hybridization of carbon attached to with the halogen atom. For example, halogen is attached to a carbon which is sp3 hybridized, that you can call it as alkyl halides, like haloalkanes you can say. See, if it is sp3 hybridized, we know it is an example of alkene, right? So for example, you can say ethane means what? CH3, this is ethane. So if I replace one hydrogen by one halogen, that becomes ethyl chloride. So that is having carbon with sp3 hybridization. No? So if it is sp3 hybridization, you should call it as alkane, haloalkanes. Okay. Next, if the carbon is sp2 hybridized, that is nothing but alkenes, right? So for example here, the simplest alkene we know is CH2, this is ethene, right? So one of the hydrogen is here is replaced by one halogen, let us say chlorine, CHCl. So this compound now called as vinyl halides, vinyl chloride. What I am saying, it's a considered to be vinyl chloride. What do we mean by vinyl chloride? See, whenever a chlorine atom is directly attached to a carbon which is sp2 hybridized, then you can say that compound as a vinyl chloride, okay, or vinyl halide compound, okay. Like that I have mentioned, when halogen atom attached to sp2 hybridized carbon, you can have two possible compounds. One is vinyl halide, yes, this is a vinyl iodide example, this is vinyl chloride example, okay. This classification is very important. If you know this classification only, I mean, if you are able to identify what do we mean by vinyl, allyl, then only you can do many questions, okay. Like direct questions also there, which are the following is an allyl chloride, allyl halide they will ask. How easy it is? Just if chlorine is attached to the or halide is attached to the sp2 hybridized carbon, that is alkene carbon, you can say it is a vinyl halide. What you can say? Vinyl halide, okay. Now if the same chlorine is attached onto the benzene ring, see here it is like this. See, here also chlorine attached to a sp2 hybridized carbon only, but this is in the benzene ring right now. So you should call them as aryl halides. What you can call? Aryl halides, okay. Now look at here, when a carbon is from sp3 carbon, that is something like CH3, CH2, Cl, yes, you can call it as halo, like chloroethane, like that. Now there is something called allylic halide. What do we mean by allylic halide? See what I am writing, CH2, double bond CH2, double bond CH, and this carbon is attached to one more carbon like CH2, and on this we have one chlorine. Now look at here what is happening. See, we have a double bonded carbons here, but our chlorine is not attached directly to the double bonded carbon, but an adjacent carbon between them. So chlorine, when it is attached to an sp3 hybridized carbon which is attached to a sp2 hybridized carbon, this is sp3 on which chlorine is present, but this sp3 carbon directly attached to the sp2 carbon, that is alkene carbon right now. So you can say this system as allylic system. What you can say? Allylic system, okay. So allylic halides are highly allylic carbocations. There is some reactivity, yes, when we are discussing about reactivity I will explain that points, now no required. So the next one more compound is called benzylic halides. So it means if there is benzene ring, if directly chlorine is attached, means you are saying phenyl like aryl halides, like that. Now, so now see there is a slight difference. Now on this benzene ring I am attaching one CH2 group here, okay. On this carbon I am inserting one chlorine. So this kind of system, whenever there is a see this, whatever the carbon you are seeing on this benzene ring, you should call it as benzylic carbon. What you can say? This is benzylic carbon. So on benzylic carbon any chlorines are attached, then you can say any halides are attached, benzyl halides you can say, okay. These are allyl halides, benzyl halides. So you can remember allyl, benzyl are of one type, vinyl, aryl are of another type. Okay, these are the two different types. Vinyl aryls you will get when it is sp2 hybridized carbon, and allyl benzyl you will get when it is sp3 hybridized carbon, that is at sp2, this is at sp3. Okay, this is a small difference. You should remember to identify which is vinyl, which is allyl. Okay, now let us see one direct question. First of all, before discussing other topics, let me show you one question that is directly from discussion of this allyl, vinyl, all these things. See, look at this. This is a NEET question asking about the given compound is an example of, which type of example it is. Those who are in the comment box, I mean live session, can answer me what is your answer for this particular question. See, what type of halogen, like what type of compound the given compound here is. Just tell me based on your understanding. Yes, guys, you can answer whether it is wrong, right, no issues. Yes, just tell me your answer in the chat box. Do not worry about whether it is right, wrong, just give me your answer, that's it. So how it is attached, check here once. Halogen atom attached to a carbon, this carbon is now sp3 hybridized carbon right now. So this sp3 hybridized carbon which is attached to a, directly attached to a sp2 hybridized carbon. It means this kind of systems, when an sp3 hybridized carbon which contains halogen, the adjacent carbon to that will be sp2. So if this is a system, you can say it as an allylic system. What system? Allylic system. So where do we have that option? See, allylic halide is your perfect answer for this question. Second option will be your answer for the question, right? So in the similar way, if I ask for this, just tell me what about this compound? What is the best suitable answer to explain this or to give this, and or what classification it goes? Just tell me. Yes, second option is perfect. Perfect it is. And tell me for this, now what will be your answer for this compound? What is a suitable answer for this compound? Which type of system it is? Whether it is arylic, allylic, vinylic, benzylic, based on the discussion whatever we did till now. Yes guys, those who are in live session can answer me, no issues. Yeah, look at here, chlorine atom again here also attached to sp3 hybridized carbon right now. So this sp3 hybridized carbon is attached to the benzene ring, right? So this kind of systems are called benzylic halides. What I told you? Benzylic halides. Remember this, benzylic halides. So for this question, this will be your answer. So now one more structure I am writing. Right. Someone in the option? Yeah. So now look at this. One more question I am giving you here. Just see, tell me directly what will be your answer for this. Chlorine is there. Chlorine is there. Within the molecule, I am just creating allylic position, benzylic position, vinylic position, and arylic position. Just tell me what will be your cases. Here I am saying this is A, this is B, and next one here. Do not scare by looking at the structure. Try to answer me what type of chlorides all these are. Just I am giving A, B, C, this one, this chlorine is C and this chlorine is D. Okay, let me write this structure properly so that you won't feel confused. This is D. Tell me. So A can be an example of which of these four options, B can be an example of which of these four options, C can be an example of which of these four options, and D can be an example of which of these four options. Like that, just give me your answers for these four compounds. Yes, anyone in the chat box? Deepansh in the chat box, anyone? Whatever you are thinking, those are right only, just express your answer, that's it. Yeah, look at this. When it comes to A, see halogen atom directly attached to the benzene ring, now phenyl ring, right? So whenever it is directly attached to the phenyl ring, you should call it as aryl halide. What you can call? Aryl halide. So the first option here is, first A compound here is this chlorine carbon bond is called aryl halide bonds here. Okay. Some disturbance here. Yeah. So now we will be discussing about the other parts of the haloalkanes. Okay, hope whatever we discussed here are clear. Now let us discuss the remaining things here. So I hope you know about IUPAC nomenclature here. How can you write the IUPAC nomenclature? It's very easy. Look at here, it's very easy. See, when you have alkyl halides, like there is two types. One is common name, another one is IUPAC. Common name, you just say alkyl halide. Like how many carbons are there? 1, 2, 3. So propyl bromide. So N-propyl bromide is its common name. When it comes to IUPAC name, first you should use halides as a prefix. Okay, so for bromine it is bromo. What is the position of bromine? 1, 2, 3, right? So 1 bromopropane. What you can say? 1 bromopropane. So this one 1, 2, 3. So 2 chloropropane. What you can say? 2 chloropropane. So 2 chloropropane. It is its IUPAC name. Now what about its common name? So whenever we have this kind of system, like this kind of system, you can call it as isopropyl. What you can say? Iso group, that is isopropyl chloride. You can say this kind of system as iso. Okay, isopropyl chloride. Okay, the next one here, if you see what could be your IUPAC name for this, start numbering from this side because substituent is here and this is the second substituent. So 1, 2, 3. So you can simply say 1 chloro 2 methyl propane. 1 chloro 2 methyl propane is its IUPAC nomenclature. When it comes to common name, see it also contains this kind of system. So isobutyl. Why butyl? 1, 2, 3, 4. 4 carbons are there means butyl now. So but it is in iso structure. So isobutyl chloride. What you can say? Isobutyl chloride will be your answer for this question. Okay, right. This is clear now. Is there any confusion in understanding this? Any confusions here? No, right. When it comes to aromatic rings, so just see when bromine is attached onto the ring, benzene ring, so you simply say bromobenzene. IUPAC name is what? Bromobenzene. Even common name is also bromobenzene. Okay, and when it is having dihalo substituents, it means bromine. What is the position? 1, 2, 3. 4, 5, 6 like this. If you see 1, 3 dibromobenzene is its IUPAC name. 1, 3 dibromobenzene is its IUPAC name. When it comes to common name, so you can see 1, 2, 3 third position now. So just remember 1, 2 positions are called 1, 2 and 1, 6 positions here. All the positions are equivalent when there is no substituent. But when there is substituent on benzene ring, so 1, 2 or 1, 6 positions are considered to be like see monobromination is there now. So with respect to this bromine, this position and this position are equivalent. That is what I am saying. 1, 2, 1, 6 are called ortho positions. Okay, and 1, 3 is there now. 1, 2, 3. So 1, 3. This side 1, 3 only. 1, 2, 3. This 1, 3, or if you want to number like see 1. How I am numbering? Just see here. 1, 2, 3, 4, 5, 6. The same way I can number it from here also, we'll get similar type of numbering, right? So whenever you are getting this 1 comma 3 and 1 comma 5, they are same only now. So 1 comma 5 positions, 1 comma 3 and 1 comma 5 positions are considered to be meta. What I am saying, these are meta, okay? And one more position we have is exactly opposite. So this here, so 1 comma 4 position, 1 comma 4 position is called para. What you can say, para position. Okay, remember this. 1 to 1 6 are called 1 to 1 6 are 1 to 1 6 are called ortho. 1 to 1 3 and 1 5 is called meta, and 1 6 and 1 4 is called para. That's it. These are the things you need to remember here. Right. Sanskar, right, it is true, whatever you are saying in the chat box. Okay, so this is 1 comma 3 dibromobenzene, or the common name is given as 1 comma 3 position. See, just remember M looks like 3, right? So 1 comma 3 position is nothing but meta. Just remember, meta dibromobenzene is our 1 comma 3 dibromobenzene. Okay, that's it. Now for ortho, what is the name for ortho dibromobenzene? 1 comma 2 position, right? 1 comma 2 dibromobenzene is our ortho dibromobenzene. That's it. Okay, right. So this is symmetrical tribromobenzene here. What about nature of CX bond in the given compound? Nature of CX bond, it means we know halogens. If I take alkyl halides like CH3, Cl I am writing. How this structure will be, just same here, the carbon hydrogen bond is less polar, I can say non-polar also, okay, almost equal electronegativity values, less difference. But carbon and chlorine, there is difference, okay. We can say this is a covalent bond, but it is a polar bond. So I can say polar covalent bond, it is polar covalent bond, okay. And how it will polarize is polar bond we are saying, so it will be partial negative charge on chlorine and positive charge on carbon, okay. It's a polar covalent bond, okay. So now if you observe the polarity values over here for different halogens, if I have carbon fluorine bond like methyl fluoride, methyl chloride, methyl bromide we have taken, so check their bond length here. What happens bond length here? Same size na fluorine and carbon, so almost same size, like 2p orbital overlapping, so that causes to be more strengthy bond, like small orbitals, small size orbitals here, so bond will be very strengthy, okay. That's why its bond strength, if you see bond enthalpy value, if you see 452, okay. So as we do move down the group, what happening here, fluorine is small size, chlorine little bigger, bromine little more bigger, and iodine is little more bigger, okay. But carbon size is small only in all the cases, same. So if there is a large size difference, what I am saying, there is a large size difference, what happens to bond enthalpies? That due to large size difference, overlapping will be very poor, so due to that bond easily breaks, okay. That's why bond enthalpy of carbon iodide is very less, that is just 234 in methyl iodide, okay. So down the group bond enthalpies decreases, remember this. Next, what about bond lengths here? Down the group increases. Why? Because iodide ion size is bigger, so down the group bond length increases, okay. So now what we got to know, this CX bond is a polar covalent bond right now, so there will be some charge generating here, it means there is some dipole moment right now. So how can you calculate dipole moment? Mu is equals to charge into distance. So what is the distances here? These things. So it means we need to compare this, we need to take consideration of charge as well as charge. It means charge here means the polarity is different now, where it will get more polarized, fluorine case. That's why considering both charge difference as well as distance, we got dipole moment values like this. So if you consider methyl chloride is greater, then next methyl fluoride. Why methyl chloride is more? Because it is polarizing the bond, but lesser polarizing than fluorine, but bond length is more for which one? chlorine when you compare with the fluorine. So together considering, we are getting methyl chloride bond dipole moment will be more than methyl fluoride, and the next this one. So what is the order we got here? Methyl chloride, then next methyl fluoride, and next methyl bromide, and least is methyl iodide. This is the order of dipole moment mu. Okay, right. Ram in the chat box. Hello sir. Hello dear. Then next here, solvents. See, in order to understand the chemical properties, I mean chemical reactions of haloalkanes, we need to know the solvents also. Like what are the solvents we have? Polar solvents, non-polar solvents. How can we say polar, non-polar? If the dipole moment in the molecule is completely zero, then we can say it is non-polar. Dipole moment, for example, CCl4 you can take. Say non-polar. Why non-polar? See, because if you write the structure of this molecule, what happens? The dipole moment, see the bond polarity is towards chlorine, so partial negative charge on chlorine, positive charge on carbon. Like that, every side we have like the same thing, like this, but they are in opposite direction. Check. Okay, if they are in opposite direction, now what happens? Overall they will cancel out each other because dipole moment is a vector quantity, so mu becomes 0. So for non-polar molecules, what I am saying, dipole moment mu value will be 0. Okay, so now tell me one example for polar solvents. Water. So water can be considered to be polar because these bond dipoles will be like this, like this. So it can be polar. Now in the polar solvents we have two classifications again, polar protic and polar aprotic. What do we mean by protic and aprotic? Polar protic means those solvents which can donate hydrogen bond. They can have hydrogen bond donor site. Hydrogen bonding should be there, and particularly they should have hydrogen bond donor sites. What I am saying, hydrogen bond donor site. For example, I am writing acetone. Look at this structure, acetone you are writing. Can it form hydrogen bonding or not? Within the acetone it cannot form, but if I have acetone and water molecule, yes, here it is possible. How it is possible? See, between water molecules hydrogen bonds get polarized like O minus plus. So between this hydrogen of water and oxygen of acetone get attracted like this. So this is called hydrogen bond. So due to this hydrogen bond, we can say it is polar and protic. But which is protic here, which is aprotic? See, okay, so this is about polar protic and polar aprotic solvents. Okay, this is basics you need to start. You need to know before starting the class itself. Right. Now let us start our discussion on preparation of alkyl halides. So first preparation is from alcohols. So we can prepare alkyl halides from different ways. The first method is from alcohols I am saying. Okay, so these are some important methods. You can take them together like a short notes so that it will be useful while revising. Okay, so now what I am saying, to alcohols if we add HI, what I am HI, like HX means it can be HCl, HBr, HI, like that we are doing. Okay, now what happens, this OH group and H plus from this acid will be removed as water, and in the place of OH we can replace with the halide. So it is very simple. Look at here, I am writing here ethyl alcohol CH3 CH2 OH. To this I am adding HBr. What I am adding? HBr. So tell me, HBr is an acid or a base? Acid. Just remember, this point is very, very important. Check here. What I am writing? HF, HCl, HBr and HI. So if you observe, these are halogen acids. What I am saying, these are fluorine, chlorine, bromine, iodine, because all these are halogens right now. Hydrogen is present, HF, HCl, all these are halogen acids we can say. But out of these four, which is stronger acid I am asking? See, we know generally we will be using HCl as an acid in our normal discussion. But you know HBr and HI are stronger acids than HCl. Which is stronger acid? Which is stronger acid out of these four? HI is stronger acid. Why? Because just see, when I say acid, that what it should do? It should donate H plus ion. It should release H plus ion. So this releasing of H plus ion is very easy when that bond is weaker between these two, hydrogen and halogen. If that bond is very weaker, then hydrogen atom comes out easily as a H plus ion right now. So now if you see, iodide ion size is very bigger, iodine size is very bigger, hydrogen size is very small. But here both hydrogen, fluorine almost same right now. So due to that reason, overlapping will be very strong. Therefore, if overlapping is very strong, the bond is very strong, will it breaks easily? No. So that's why HF is weaker acid and HI is stronger. Why it is stronger? Due to its very less bond dissociation energy. H plus ion comes out easily. Okay, after this we will discuss few more points. What is the acidic nature of these halides? HI is stronger, the next HBr and the next HCl and least is HF. Okay, so now here HBr is stronger acid now that provides H plus ion. That provided H plus ion is taken by whom? Tell me here. That H plus ion can be taken by our OH group. So OH, H plus, removed as water now, H2O, removed as H2O. So if it is going out as a H2O, our bromide ion can attach here. So you will get CH3, CH2, Br plus H2. Yes, H2 like this. Okay, so that is what happening in the first case. Okay, in the second case, if you see ROH, alcohol with PX3. PX3 is nothing but something like PCl3 you can take. Now how many chlorides are there with the phosphorus here? 3. So one PCl3 can react with 3 alcohols. How many I am seeing? 3 alcohols. On each alcohol there is one OH group now. So replace this OH group with this chlorine. Now what happens? H3PO3. That's it. So it means let us take it separately and we will discuss here. CH3, CH2, OH plus PCl3 I am taking. So tell me what I am saying. So it follows SN2 mechanism. I will explain about SN2 mechanism and all. Okay, now what happens? One OH just exchange these things. Okay, like that chlorine can be given to that. So what happens here? Here CH3, CH2, Cl. Okay, like that. How many chlorines can be contributed by phosphorus? 3. So 3, give it to 3, this one. So 3 alcohols I am taking. So it is giving 3. So each OH given to this phosphorus, like that how many can be given? 3. So you can say POH thrice right now. So POH thrice should be not written like this, actually it should be H3PO3, H3PO3, orthophosphorus acid. What is it?
Orthophosphorus
Acid, like that. Place of PX3 we have PX5. PX5 means like PCl5 you can take.
Sir, but other one.
Okay, see, let us take alcohol and treat this with PCl5. What I am saying, treat this with PCl5. So PCl5, what is the geometry? Trigonal bipyramidal geometry. So in this PCl5 there are 3 chlorines in equatorial positions and 2 are in axial, like this, above and below. So these above below chlorines are there now. This is a planar molecule and this is non-planar with respect to axial bonds. This above and below one. Okay, so this can be removed easily. It means these 2 chlorines are weaker. So whenever you are using PCl5, what happens? 2 chlorines comes out. Okay, so you take one alcohol. I am taking one alcohol, treating with what? PCl5. Now what happens? Alcohols converts into alkyl chloride. Okay, so it means how many chlorines we have taken? Just one I have given. One more is there now, that will react with this H and forms HCl. Okay, and this oxygen is taken by our phosphorus. So how many chlorines we have taken from PCl5? 2. It means remaining how many are there? 3. So it will be PCl3 and that oxygen is taken by our phosphorus. So POCl3 will be produced. Okay, alkyl halide, HCl and POCl3. These are the things here we are seeing, right? The next one is same alcohol. So same alcohol, let us say ethyl chloride I am taking here, CH3, CH2, OH. I am treating this with SOCl2. SOCl2 is called thionyl chloride. What I am saying? Thionyl chloride. So this is a very best method for conversion of alcohols to alkyl chlorides. What I am saying? Conversion of alcohols to alkyl chlorides. Okay, why this is best method? See, just take this OH and place there chlorine, like a substitution only. Okay, I will explain the mechanisms, but first write these reactions. Cl like this. So now what is happening? It is giving chlorine. Like that, SO and this O forms SO2. What it is forming? SO2. And this hydrogen and the other chlorine here, HCl. See, HCl, SO2, both of them are gases only now. So when the product is formed, these gases goes out easily, escapes easily, so that our product will be there. Okay, we can collect our product easily. Okay, that's why this is one of the best method for conversion of alcohols to alkyl chlorides by using thionyl chloride. Then next one, same thionyl chloride only I am using, SOCl2 only we are using, but in presence of pyridine. So here you won't see much difference, but when there is a chiral center, you will get the difference. I will tell you what is that chiral center and all. See, here also same product, CH3, CH2, Cl. This is fine, but let me show you one example here, what I am writing. Just see, OH group, like this I am writing. So this is chiral carbon or not? Just check. Chiral means what? There should be 4 different groups. Yes, do we have or not? See, this side one group, this is second group, third and fourth one is our hydrogen. So we can say this carbon as a chiral carbon. Whenever there is a chiral center, so if you are treating this with simple SOCl2, what I am saying, simple SOCl2, and there is one more is SOCl2 in presence of a base like pyridine like base. Okay, so now what the difference here? What makes the difference? See, whenever you are taking SOCl2, simple SOCl2, this mechanism name is called SNI, retention of product takes place in these intramolecular nucleophilic substitution reaction. Okay, so what happens here, you will get a product like this. So what you are seeing, wherever, see, above the plane OH group is there, the product also above the plane chlorine is there. So this kind of products are called retention products. What I am saying? Retention product. Retention of configuration you are seeing. What do we mean by retention of configuration? I explained you about RS nomenclature previously. What is that? So OH group now. So if you see, you will get one particular clockwise, anti-clockwise direction, same rotation will be there. Okay, simple. OH group above the plane, halogen also above the plane. That's it. Retention configuration. When I say inversion configuration here, what happens if OH group above the plane, our chloride ion comes from below the plane. So you can write the product in this way. Okay, so what is this? Inversion of configuration. See, sometimes when we are studying about stereochemical aspects, okay, there is lot of difference. Okay, so it means, see, when you are applying it in advanced level chemistry, it means advanced level means synthetic chemistry you are doing. Okay, there are some compounds. See, there are some compounds like you know, there is a big disaster itself we have, that is called thalidomide disaster. What I am saying? So that thalidomide disaster is, see, it means scientists derived one compound, its name is thalidomide. So that compound is used for pregnant women. For what purpose? For morning sickness. For what purpose? Morning sickness. To overcome this morning sickness, that thalidomide tablet will be given. Okay, now what happens is, at that time they are not aware much about this R and S configurations of or stereochemical approach of this thalidomide compound. Okay, so when they synthesized this compound, they have got extracted mixture of R and S configuration product. What they extracted?
Mixture of
R and S. But out of these two, only R configuration, only one configuration is medicinally active. It means that will work for that morning sickness. One more configuration is there now, this S configuration, the other one. Okay, so that will be causes dangerous health hazards, but they are not aware about that much. Okay, so now what happened, whoever the pregnant woman taken this thalidomide tablet, the newborn babies will be there now, they got all defects, birth defects have been observed there. Almost some 10,000 people got affected by this tablet. So that's why it is considered to be thalidomide disaster. Now how these two compounds, thalidomide R and S configuration are differ? See, for one compound, that nitrogen atom in that structure I will show you later, one will just search after going home, you just search about thalidomide disaster, you will get to know. So one nitrogen atom will be above the plane, here below the plane. Same whatever the compound you are seeing, I mean like this, there is a stereochemical difference is there, that's it. So that small difference causes very big disaster. Okay, so this is the importance of studying stereochemistry and the stereochemical approach. Okay, right. Okay, the next here, this is clear now. So what are the reactions we have made? So these are the short notes, you can take it. And the next one is called a Lucas reagent. What I am saying? Lucas reagent. What do we mean by Lucas reagent? Tell me. Lucas reagent means it's a combination of anhydrous ZnCl2. What I am saying, it's a combination of anhydrous ZnCl2 and concentrated HCl. What I am taking? Anhydrous, it means there should not be any water. Anhydrous ZnCl2 plus concentrated HCl. So this mixture is called Lucas reagent. What is the use of Lucas reagent? So it converts alcohols to alkyl chlorides. How it will be converting alcohols to alkyl chlorides? Okay. Now they will ask what is the reactivity of alcohols with the Lucas reagent. Okay. So we have 3 degree alcohol, 2 degree alcohol, 1 degree alcohol. So what do we mean by 3 degree, 2 degree, 1 degree? See, the alcohol group attached to the carbon, if that carbon is containing 3 alkyl groups like this, any 3 alkyl, 3 carbon atoms are attached like this, then you can say it as a
third degree
tertiary. Okay. Now if to the alcohol attached carbon there is one hydrogen and remaining 2 positions are something like occupied by these alkyl groups, so secondary. Then next, if there is only one alkyl group attached to the alcoholic group containing carbon, primary. Okay. So now out of these 3 alcohol, who will react faster with this Lucas reagent, they will ask. So tertiary is more reactive, then secondary, and least is primary. So what is the reactivity order of alcohols? 3 degree, 2 degree, 1 degree. See, the difference will be like this. 3 degree alcohol, the tertiary alcohol, upon adding this Lucas reagent, just shake it like this, within 4-5 seconds you will get turbidity. What you will get? A turbidity. So looking at that, yes, you can identify, yes, this is a tertiary alcohol. So that's why it is reacting very faster with a Lucas reagent. And the next secondary will take some like minutes, like 5 to 10 minutes like that. So depending upon the time, speed of reaction, we can able to identify whether the given alcohol is tertiary, secondary, primary. Okay, we can distinguish them. Primary, secondary, tertiary alcohols can be distinguished here. Okay, is this clear? And the next one, you should ask me, sir, why only concentrated HCl? Why not dilute HCl? Okay, so you might be getting like this doubt. Okay, here, if you use dilute HCl, the nucleophilicity nature of chloride ion will be decreased. What I am saying? Nucleophilicity nature of chloride ion will be decreased. That's why we are not preferring dilute. What we are preferring? Concentrated HCl or dry HCl. What I can say? Concentrated HCl or dry HCl. So dry HCl is nothing but gas. It's a pure HCl gas. So both can be used here. So but Lucas reagent means what you can remember? Anhydrous ZnCl2 and concentrated HCl. Okay. Okay. So chloride ion, if we take dilute one, what happens? It will get solvated and its nucleophilic nature decreases in the aqueous medium. That's why we are preferring concentrated, not a diluted one here. Okay, clear now? Lucas reagent test, right. The next one here we will be discussing see here what I told you. Generally, alkyl halides are prepared from alcohols by replacement of OH group by a halogen atom by nucleophilic substitution. Here dilute HCl is not used because chloride ions get hydrated and its nucleophilicity get decreased. So dry HCl or concentrated HCl is used. Okay, I'm saying this one, when you directly treating alcohols, when you are directly treating alcohols with HCl, that HX process we discussed now, there you should take this as a concentrated one or dry HCl. Okay, it should not be a diluted one. So other process we have Lucas reagent. What is that? Anhydrous ZnCl2 plus concentrated HCl. These are the two things you can use for conversion of alcohols to alkyl chlorides. Okay, in case of tertiary alcohol, reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature. The reaction of primary secondary alcohols with HCl requires a catalyst. What is that catalyst we are using? ZnCl2. That is a Lucas reagent we discussed. Okay, right. Then next here, see here, tertiary alcohols will give turbidity instantly, secondary give within 5 to 10 minutes, primary no turbidity. We need, it requires heating. Okay, so can you answer me this? Which of the, you require little more time for answering this. Let me give you few more things to discuss. See here, what I told you, tertiary is more reactive now, right? So let me give you few more explanation, then you can go through that. So here, order of reactivity of alcohols with a given halogen acid. Okay, see, we are discussed about HI, HBr, HCl, HF, which is more reactive alkyl hydrogen halide here, H, which is stronger acid here. So that will be more reactive. This is a reactivity order. Okay, but when it comes to iodine, we required some oxidizing agent. I will tell you about this. But if I want to compare between HCl, HBr, which is more HBr. Okay, up to here it is clear. Now hydrogen halides are clear. Now next, order of reactivity of alcohols with a given halogen acid. It means we have different alcohols now, primary, secondary, tertiary alcohol. Which is more reactive out of that? Tertiary. That is what we have seen, turbidity within seconds. Okay, that's it. Okay, the next one is, when I am using HI, see, read this. Alkyl iodide may be obtained by heating alcohols with sodium or potassium iodine in 95% orthophosphoric acid. So what we need to use along with our HI, we need to use 95% of orthophosphoric acid with potassium iodide or sodium iodide to get your alkyl halides, alkyl iodides. Okay, phosphorus halides already discussed, this is also done. From hydrocarbons, it means hydrocarbons means what are the things we have, like this is a hydrocarbon or not? So first of all you take this simple one, you just wanted to convert given alkene to alkyl halide. So what do we do? So we can replace hydrogen atoms by this chlorine, right? So you can do CH3, substitution mechanism you can follow here, like this we will get. Mono substituted product is getting. So we can replace all hydrogens with chlorines also, right? For example, methane I am taking. So now what happens, tell me here, chlorine I am using. So what happens, tell me? So if I take chlorine as excess quantity, what I am taking excess here? Chlorine. So if chlorine gas is taken excess, all hydrogens can be replaced by chlorines, so that you will get CCl4. And how many hydrogens are there here? 4. So it will form 4 HCl. Okay, this reaction takes place in presence of sunlight. Where it takes place? Sunlight, or suitable frequency is required here. Okay, and one more thing you can remember, if I take methane as excess quantity, what I am taking excess here? If I take methane as excess quantity, major product formed here will be CH3Cl. If I take chlorine as excess, this is my major product. If I take methane as excess quantity, methyl chloride will be formed as a major quantity. Okay, sir, you are saying major, minor. It means yes. Why? Because see, out of these 4 hydrogens, I can replace all 4 hydrogens with the chlorine, we will get CCl4. Or I can replace only one hydrogen with the chlorine, we will get this one. Or I replace 2 hydrogen with the chlorine, we will get CH2Cl2. Or I can replace 3 hydrogen with the chlorine, so it will form CHCl3. So these are the 3 different possible products are there now. Yes, mixture of products will be formed, but depending upon the situation you are taking here, if chlorine is excess, CCl4 is major quantity, but mixture of products are obtained, but this is major. Similarly, if I take methane as excess, methyl chloride will be major. These byproducts are also there, major quantity is this one. Okay, is this clear? And one more thing, what is the mechanism followed during this reaction? It follows free radical substitution reaction mechanism. What is that? free radical substitution reaction mechanism. So what do we mean by free radical substitution reaction mechanism means, see here we are using chlorine now. In presence of what? Sunlight we are doing this reaction. So take chlorine like this. So chlorine has lone pair electrons on it, right? So whenever you are treating with a suitable frequency like sunlight I have mentioned, now what happens is there is slight repulsions between chlorine atoms due to the lone pair repulsions here, electron density. Now whenever you are supplying this frequency, suitable frequency, this bond gets cleaved into two equal pieces. Okay, we can call it as homolytic cleavage, so that it will generate chlorine radicals. How many radicals generated? 2 chlorine radicals. Okay, so now these 2 chlorine radicals starts reacting with our methane. Okay, so the first step here you have seen, this step is called chain initiation step. What I am saying? Okay, so for production of chain initiation step, we need to use symmetrical reagent. What is it? See, chlorine. It's a symmetrical bond or not? So symmetrical bond upon supplying suitable frequency breaks into 2 equal halves and generates free radicals. What they will generate? Free. So free radicals are highly reactive. They are highly reactive. So when they are highly reactive, so that radical will attack on our hydrocarbon. When it is attacking hydrocarbon, what happens, tell me? So it will abstract a proton from our methane and forms methyl radical plus HCl. What it is forming now here, see? Methyl radical. So now methyl radical will be becoming reactive right now. So methyl radical, what it will do? These methyl radicals will react with chlorine now. With what? They will react? So chlorine, like this. So now what happens? This radical and this chlorine forms methyl chloride plus again Cl radical. Like this reaction keep on goes on. So we can say these steps as chain propagation steps. What I am saying? It will keep on going. Okay, right. Now what is forming here? Chlorine radical right now. So now there should be stoppage of this reaction, otherwise it's keep on going. Now what are the possible ways to we can stop these? Whatever the chlorine radicals are formed, that will react with themselves and forms chlorine gas, or whatever the methyl radicals are formed, that should react with themselves and forms ethane. Like this byproducts are formed. So this is how reaction will get stopped. So we are stopping the reaction now. First step is chain initiation, next is chain propagation. You are terminating the reaction. So you can say this is chain termination reaction. Okay, 3 steps in free radical substitution. First step is chain initiation, next step is chain propagation, and third step is chain. That's it. Okay, now they won't ask about this. Mostly the questions are like this. Just listen. What is the name of this compound? Propane. Upon chlorination, what are the possible products formed? Upon monochlorination of this propane, possible products are, see here you have methane, methyl, here also methyl, and this is in between methylene is there. Okay, these terminal groups are same now. It means you can replace one hydrogen from here or from here, that gives a product like this. Yes or no? So this is of one type of product. So because all these hydrogens are same. So let us say this is A type of product. Okay, or you can replace this hydrogen, one the chlorine, then you will get this type of product. Let us say this is B type of product. So you got A type product, B type product. Okay, so how many types of products we got? 2 types right now. So now I will be increasing little more. Now tell me, this reactions takes place in sunlight. Yes, tell me fast. Now how can you see how many types of products formed? Just look at here, this methyl group of butane, this methyl group are same, and this methylene group are of same type. Okay, so let us say these terminals are of A type, both of them are same methyls, and these internal methylene are B type. So now replace one hydrogen from here or here, both of them give same product, that is nothing but chlorine. Okay, and center here if I replace this one right now. So I am saying this is A type product, this is B type product. So how many you are seeing? Is there any other way to get another product? No. So what will be your answer? Yes. So but if you look at this compound A, you just tell me what about chiral carbons? What do we mean by chiral center? Carbon with 4 different groups right now, like A, B, C, D should be there. So there is no chiral carbon in A because 2 hydrogens only there here. But in B, if you observe, this is methyl group, this is ethyl, this is chlorine, and one more is hydrogen. So you are getting a chiral carbon here right now. So now chlorine can be above the plane, chlorine can be below the plane. So 2 types of products are possible here. So this is called chiral center now. So whenever there is one chiral center, so number of stereoisomers possible is 2 power n, that is 2 power 1 because n represent number of chiral center. So you will get 2. One can be R isomer, other can be S isomer. So your A type products are 1 and B type products are 2. So total isomers possible are how many now? 3. So this is how you need to answer the question. Okay, is this clear or not? Clear or not? Tell me fast. Clear? Right. Now tell me how many possible products for this compound? Take it as a homework and give me your answer in the next class. And guys, this is a very repetitive question in your exams. Very repetitive exam question I am saying. Okay? No. Tell me all number of possible monochlorinated product. What I am asking, number of possible monochlorinated products. Okay, this is your question. Next one, you need to answer me this. See, just tell me, first step is what? We need to identify types of hydrogen atoms present in the substrate. See, this one are of same. And what about this? Same. B here. See, these are primary, this is also primary, but these two methyl groups attached to a tertiary carbon right now. But this methyl group is attached to a secondary carbon. Are they same now? These methyl groups are different. So these two are of A type methyl groups. This is a B type methyl group. Now this is a C type, and here we have one hydrogen. So this is a D type. Like this, classify first. Okay. Then next, you replace one of the hydrogen from this A type carbon, then from B type. Like that, you write the possible products. If there is any generation of chiral center, then you will get a 2 isomers. Like that, you write possible products and tell me your exact answer in the next class. Okay, you take time and try it and tell me. Okay, we will discuss the same thing in the next class based on your response. Okay, right. The next one here is, see, I am taking butane and I am asking you to halogenate this with fluorination, chlorination, bromination, iodination in presence of sunlight. So which is more reactive? It means halogenation, reactivity of halogenation or reactivity of halogens in free radical substitution reaction. What I am asking? Reactivity of halogens in free radical substitution reactions. Tell me. F2 is more violent. Okay, we cannot even control the reaction. That's why fluorination of fluorination of hydrocarbons cannot be preferred. Okay, fluorination cannot be done because it's highly reactive. Okay, then next chlorination, next bromination, and least is iodination. Okay, this is a reactivity order. What is it? It's a reactivity order. Okay, and you know I2 is very slow and this is reversible, slow and reversible. So if we want to do iodination, we need to use some oxidizing agents like HiO3. In presence of HiO3 we can do. Okay, normally it is very slow and reversible. Okay, so it means free radical substitution reactions of halogens is preferred only for chlorination and bromination. It is preferred for chlorination and bromination. So which is more reactive out of these two? Chlorination is more than bromination. So I am saying if a species is more reactive, that is less selective. What I am saying? Selective. If a species is more reactive, that will be less selective. What is this selective and reactive? Just look at here what I am saying. Selective, not stable. More reactive, less selective. It means I will tell you, just see here. So if you observe methyl, 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 all these methyl groups are same or not? What about this hydrogen? Tertiary hydrogen. So this is a tertiary, this is primary, right now. So how many types of hydrogens are there? Two types. First of all, in free radical reactions, you need to identify, if you want to get number of types of products, you need to identify number of types of hydrogens present in the given compound. So how many types of hydrogens present? Two types. So now simultaneously I am doing chlorination first, then next followed by bromination. First what we are doing? With this compound, I am doing my reaction of chlorination. What are the possible products? Tell me fast, do not waste the time. I can replace one of the hydrogen from anywhere from this terminal sites and I place chlorine, or I can remove this tertiary hydrogen so that I will get a chlorine at the middle. Right now these are the two possible products. Similarly here what happens? We will get bromine here or bromine here. Now what I am asking is, what is my question is, which is major product out of this? Which is major product I am asking?
Primary, terminal.
Remember what I told you, more reactive to less selective. Okay, so which is more reactive? Chlorine is more reactive than bromine. Okay, it means chlorine is a less selective, it is more reactive. It means less selective means wherever the reactive site is there, chlorine goes and react there. What I am saying? Wherever there is reactive site there, chlorine goes and react. See, how many reactive sites are there for primary centers? See, this can be primary center, this is also one. See, these three are same type or not? So how many reactive sites are there? 3. I mean center one also reactive site, but same type of reactive sites are how many? 3. So at these 3 sites chlorine can react and generate this type of product. So it means which is major product when chlorination is taking place? Terminal side, because that same type of hydrogens are more. Okay, I will tell you exact value also how to calculate, but try to understand the concept. Okay, but this reactive site is only one we have. So it means this is less selectively reacting here, more selectively, I mean more reacting at this terminal side when you do chlorination, when you compare with this. Okay, when you do chlorination, this will be your major product. Okay, when you do bromination, and this is minor product in chlorination, when you do bromination, the case is reversed. So this will be major and this will be minor. So I will tell you exactly what you need to remember here is, there is types of hydrogens, like it can be tertiary carbon hydrogen, it can be secondary carbon hydrogen, it can be tertiary, primary, secondary, tertiary carbon hydrogen, right now. So I can do now chlorination or I can do bromination. So whether if there is only primary type of hydrogen, both can react one time. Okay, but when I have secondary, so this will react around 3.6 times. How many times? But this will react 80 times. It means selectively where it is reacting? Bromination is taking place more selectively secondary when we compare with the primary. And you remember this, tertiary carbon hydrogen is there, means chlorination takes just 5 times, but bromination takes around 1600 times. How many times? It means bromine is selectively choosing which site? Tertiary carbon hydrogen site is chosen by bromine. That's why, see, in the given compound there is primary center, tertiary center. but bromine is choosing which site?
Tertiary.
Tertiary site. So how many times it is reacting? So that's why your major product will be here bromination. In cases tertiary bromide is major. Okay, but when you are doing chlorination, see, you got this is tertiary hydrogens are only just 5 times, primary hydrogen is 1 time. It means, sir, how you are saying that is major minor? I will tell you here. Come, see, how many primary hydrogens are there in the given compound?
9.
3, 3, 3. 9 primary hydrogens are there. So 9 primary hydrogens, each one can react one time. So because reactivity is 1 here, so it is 1. So you will get 9. Okay, percentage I am doing here. Now how many tertiary hydrogens are there? 1 we have. What is its selective reaction here? 5 times. So you will get 5. So total percentage is how much? I mean total addition is how much? 14. You got this 14 now? So it means the quantity of primary product formed, if you want to measure, so what you can do? Percentage of primary chlorine formation will be equals to total quantity is how much? 14. What is the quantity of reaction here? 9 into 100. And for this one, tertiary chlorine 5 by 14 into 100, which is major quantity. 9 is bigger or 5 is bigger? So it means this is making major. Primary product is major. That's why I am saying primary is major. Is this clear? And now tell me for this one in the same manner, what I can multiply here for bromination? For these two things, tell me fast. See, there is a primary first, primary reaction. Yeah, tell me. So how many primary hydrogens are there? 9. So 9, and its selectivity is how much here? 1. So you will get 9 here. Okay, then next tertiary, what happens? Tell me. Only 1 tertiary hydrogen is there, but it reacts, selection is 1600. So total sum is how much?
1600.
Total sum is here 1609. Okay, so primary bromination is how much? Tell me here. Primary bromination 9 by 1609 into 100. But this one, tertiary one is 1600 by 1609 into 100. So which quantity is bigger? See, this is almost 99.9% like that right now. So that's why this is major in bromination and this is primary one is major in chlorination. Okay, so depending upon type of reaction, you need to choose which is major, which is minor. Everything that the possible questions they can make from here is discussed. Okay, first of all, main important point is identifying number of monohalogenated products. Second one is what? Identifying which is major and minor product. That's it. And you know one interesting thing here is we cannot use halogenation for production of halo compounds from alkanes. Why we cannot use? Because see, mixture of products we are getting. So to separate this mixture of products, it is very difficult. Right now, it is time consuming and cost also takes too much. Okay, that's why we won't prefer when we go to synthetic chemistry. Okay, we just learning this. If there is compulsion, then we can use. But what I am saying, due to formation of mixture of products, possible products, we are not preferring preparation of haloalkanes from alkanes by this free radical substitution mechanism. That's it. Okay, clear? What we discussed, tell me once fast.
Classification of haloalkanes, solvents.
Solvents.
Preparation of haloalkanes by alcohols and hydrocarbons.
That's it. Okay, fine. So remaining things we'll discuss in the next class. Okay, right, fine. So those who are in the live session can join these sessions daily so that it will be useful for your preparation also. And if you have any doubts, please feel free to write in the chat box. Thank you for watching.